Right, where did we leave off? Buffers?
Yeah.
Buffers? Okay. Well, we're going to continue with buffers. And so, what application do buffers have? The primary application for buffers is to maintain a stable pH. For example, if you were to accidentally dilute it, if you accidentally dilute an acid solution or base solution, pH is going to change. But with a buffer, you accidentally dilute it or make it even more concentrated, the buffer should maintain the same pH. Because not the quantity, it's because of the ratio. The pH of the buffer just depends on the ratio of components, and by adding water, it doesn't change the ratio of components. And the buffer should also not only be able to handle added water, but it should be able to handle added acids. Like, you could add small amounts, or depending on what the capacity is. Here's where the capacity makes a difference. Because if you have a low capacity buffer, you can't add so much additional acid, strong acid, versus a high capacity. A high capacity buffer, you could add significant quantities of strong acid. So if we add strong acid, the buffer tries to maintain its pH, or if we add strong base, buffer will try to maintain its pH. Of course, water. Buffer will try to maintain its pH. And so let's first look at an unbuffered solution. So an example would be, an unbuffered solution would be like just DI water or distilled water, or just pure water. If we have pure water, pH should be 7.00. And so what we're going to do is we're going to take 100.0 milliliters of this water and add 1 drop of 6.00 molar HCl. 1 drop is, we're just going to say it's about 0.02 milliliters. And so what's going to happen to our pH? And so in chapter 17, we're going to start off every calculation with step I. Step I is just this initial step, which is solution dilution. And so for solution dilution, what we do is we figure out what the final volume is. The final volume is 100.05 milliliters. Final volume. And then I have to figure out what the new concentrations are. And so HCl, with solution dilution, we have something called the dilution factor. The dilution factor is just its initial volume. The initial volume is 0.02, and we divide the final volume, which is 100.05. And so the dilution factor would be a 2 to 10,005 dilution, 2 parts of 10,005, or 0.02 to 100.05 dilution of 6.00 molar. And so we take our dilution factor, multiply by our concentration, initial concentration, we get our final concentration, which comes out to like 2.99, something times 10 to the minus 3 molar. All right, so our HCl was heavily diluted. Our water wasn't, water's about 100 mils, but let's see what happens to the pH. And so at this molarity of hydronium, do we have to worry about Kw? Would Kw add much additional hydronium to an HCl solution like this? The answer is no, because Kw, the most you're going to get is 10 to the minus 7, but in reality it's going to be less than that, 10 to the minus 8, 10 to the minus 9. If we add 10 to the minus 9 molar hydronium to this, is it even worth calculating how much? No, so we ignore Kw here, and then we'll just calculate the pH based on how much hydronium we get from the HCl. And so the pH of this would be the negative log of the HCl, which is the same as hydronium, which is pH of 2.52. So what happened was I went from a pH of 7.00 to a pH of 2.52. And so what we see here is that water was not really able to maintain its pH, right?
What is the example say? So the example
Unbuffered solution. Sorry, unbuffered. And so water has no buffering capacity. You add that HCl and the pH changes dramatically. In fact, it becomes about 10,000 times more acidic, 5 orders of magnitude roughly.
So that equation right there only used for water?
What's that?
Is the equation with the dilution factor times the original molarity?
No, we use for everything.
How do we take that into account when the original solution has a pH that's not?
All right, we're going to do that next.
How do you get 2.99?
I don't know. That's what they got this morning. So it's 0.02 times 6 divided by 100.05. What does it come out to?
One point
1.20 times 10 to the negative third. Is that what other people got? Oops. All right. Which gives us what's the pH here? What is it? 2.92. 2.92. Well, so we go from pH 7 to about a pH of 3, so that's 4 orders of magnitude. 4 orders of magnitude would be at 10,000 times more acidic. Thanks. So it comes out quite a bit more acidic. But if we have a buffer solution, the buffer solution will try to maintain its pH. And so let's take a look at Henderson-Hasselbalch buffers. And so we have some buffer concepts here. One of these will be something called optimum pH. The optimum pH is the pH when we have a 1-to-1 ratio of base to acid. And so in this, in a Henderson-Hasselbalch buffer, we have to have an acid, like acetic acid here, and its conjugate base, like sodium acetate. And so if we have 0.100 molar acetic acid and 0.100 molar sodium acetate, then we have equal parts of acid and base in this mixture. And so this would be a ideal or optimum scenario in which the pH of the buffer solution is going to equal the pKa plus the log of the base over acid. And so the pH is just equal to the pKa. And so the optimum pH would just be the pKa for this, because then we have a 1-to-1 mixture of base to acid. So let's take a look at some pKa values. Chapter 16. right, so here's some pKa values here. So if we take a 1-to-1 mixture, so if I made a buffer like this, I put in some iodic acid here and sodium iodate. So if I take iodic acid and sodium iodate and put them into 1-to-1 mixture in terms of concentration, it could be 0.100 molar to 0.100, so that'd be 0.1 over 0.1, or it could be 1 molar over 1 molar, so 1-to-1, or half molar, half molar. It's the same concentration, equal molar parts of acid to base. Then I'm going to get a pH of 0.80. And when you think about that, well, that's quite acidic, isn't that? 0.80. But we'll see a wide range of pHs here. And so, for example, here this is closer to 7. So if I go hypochlorous acid and something like sodium hypochlorite, 1-to-1 ratio of this, I'll get an optimum pH of 7.54. Over here, if I take something like phenol and sodium phenolate, I get a pH of 10 in a 1-to-1 ratio of those. And so these would be the optimum pHs. Just as an aside here, we can see which one's bigger, you know, Ka or Kb, depending on that pH here. So if I have a 1-to-1 ratio of hydroiodic acid and sodium iodate, then I'm looking at a competition between Ka versus Kb. And the optimum pH is 0.80. And so that means what's bigger, Ka or Kb? Well, if the optimum pH is 0.80, I'm producing a lot more hydronium than I am hydroxide. And so Ka is much bigger there. When this is about 7, then here the HOCl and the OCl minus are going to have about the same. The Ka and the Kb are going to be roughly the same. Versus phenol, you know, the pH is 10, which means the base is stronger than the acid. And so this is what causes, even though I have a 1-to-1 acid-base mixture, the pH isn't 7. The pH depends on which one's more dominant, the Ka or the Kb, and therefore I could have buffers spanning a wide range of pHs here. And a buffer is going to be a stable mixture of weak acid and weak base together. All right. Phenol is kind of an interesting acid because phenol, let's talk a little bit about structure since we're at this chart here. But phenol is an alcohol. And normally alcohols, are they very acidic like ethanol? Is ethanol very acidic? No, ethanol is not very acidic. In fact, ethanol we don't even consider an acid really. This is an alcohol. But all alcohols can act as an acid if there's something strong enough, a strong enough base to pluck out that proton. But phenol itself, water is a strong enough base to pluck out the proton. In ethanol, water is not. And so when we look at phenol, what makes phenol a decent base compared to other alcohols? And so it must have something to do with this benzene ring. In other words, the benzene ring, when we think about this, you know, when we look at alcohols, well, that's a difference because it's just what's attached to the OH group. And so this benzene ring must be an electron withdrawing group, that is, it's sucking electron density away from this, or an electron pushing group, it's giving electron density to this. What do you think? The benzene ring is an electron withdrawing group. That is, it's sucking electron density away from this, making this hydrogen more electropositive. Which is unusual because most hydrocarbons are electron pushing groups. Most hydrocarbons are electron rich. And so when you have a hydrocarbon like an ethyl group here, then it's electron pushing, making this delta plus even smaller than water, which makes it even less acidic than water. But here, this has got to be an electron withdrawing group that making this bigger in that sense. That's one way of thinking about this, if we're looking at the polarities. There are other factors that are associated with this. We'll see it when we actually do the numbers. We're going to do some numbers in the lab. There could be other factors. Maybe that's not the factor. Maybe it's the stability of something called phenoxide, which is this. But anyway, continuing with this, we see, okay, optimum pH. Now, did I talk about the Henderson-Hasselbalch equation? No? Did I think about Henderson-Hasselbalch buffers? No? Did I talk about weak acid, weak base mixtures? Yeah. Okay.
Professor,
Uh-huh.
you said that alcohols can act as acid. What are the most common characteristics that alcohols have that allow them to act as acids?
Well, alcohols in general don't act as acids. Alcohols in general don't act as acids. And so most alcohols, like methanol, ethanol, the only way they'd act as an acid is if you have an extremely powerful base, like amide or something like that, come along and pluck the hydrogen. Water doesn't really hydrolyze. Alcohols really don't hydrolyze water. Water is really not strong enough base to pluck out the hydrogen. And so when we think about alcohols in water, we think of them as being neutral. It's just, this is an unusual alcohol because this alcohol here is actually fairly acidic compared to most. And so it has to do with what's attached here. It's actually more complicated than what I say, because you know, there's got to be some kind of electron withdrawing effect here, or there's got to be some kind of stabilization, which we'll talk about. And so one thing we look at is the group that's attached here. Is an electron withdrawer or electron pusher? And so we'll take a look at that when we look at structure. We actually took a look at it before because the oxidation state on the carbon that's attached to the alcohol group is different for both of these. But let me wait until we do the lab, and then we'll talk about it in more detail. I think I skipped some stuff then, and so let me go back and talk about it. So what buffers are weak acid-base mixtures. And so weak acid, weak base mixtures, one characteristic about weak acid, weak base mixtures is they don't neutralize each other out. And so let's take a look at some examples of weak acid, weak base mixtures. An example would be something like ammonium and acetate. Ammonium, this is a weak acid. Acetate, this is a weak base. So if we had, well, weak acid, weak base, what should it do? It should maybe it should react, right? So ammonium reacts with acetate. to form what? Acetic acid and water. Did we do this? Acetic acid, not acetic acid and water, acetic acid and ammonia. Did we do acetic acid and ammonia earlier as an example? I don't remember.
We did acetic acid and sodium acetate.
Acetic acid and sodium acetate?
Yeah.
All right, that's the Henderson-Hasselbalch buffer.
That's all I have from before then, so.
Did we talk about other weak acid, weak base mixtures?
No. I don't have the acid and base mixture. We talk about acid/base mixture every day.
We did acetic acid and ammonia?
Yeah.
All right, et cetera. Let's say et cetera. Here we have to do Ka, Kb, and Kw simultaneously, right? Then we talked about amphoteric. Amphoteric would be like a sodium, hydrogen, phosphate or something, dihydrogen phosphate.
I have that. I can have that.
You do have that?
That's right in the beginning when we started.
All right.
First, I need that.
Amphoteric is going to be Ka and Kb for the same species, right? And this can be solved simultaneous. And that simultaneous is going to lead to a simple equation that the pH is equal to the pKa for the amphoteric plus the pKa for the conjugate acid of the amphoteric divided by 2. Do you have that equation? Yeah. Then the third type of weak acid, weak base mixture will be when they're conjugates of each other. And this third type is called the Henderson-Hasselbalch. It's called a Henderson-Hasselbalch buffer. All these have buffering actions. For example, this can buffer solutions as well. These are buffers. Weak acid, weak base mixtures are buffers because of how they work. Although the amphoteric isn't as stable, the mechanics will be slightly different. But in this Henderson-Hasselbalch buffer, it's where the acid and base are conjugate of each other. And so the example here would be acetic acid and sodium acetate. And so acetic acid is going to have a Ka, sodium acetate is going to have a Kb, and then we have Kw. And so the question is do we have to solve this simultaneous? Is simultaneous required? Like over here, yes, you know, this is required. So over here we have simultaneous, we have to do with Kw, Ka, and Kb. Do that. For the Henderson-Hasselbalch, is simultaneous required? You know, it's a weak acid, weak base mixture. There's a Ka, Kb, and Kw. And so let's take a look. Did I set up the Ka and the Kb for acetic acid and sodium acetate earlier?
Yeah.
Yeah. And so what was the take-home message from the Ka and Kb set up? Was there any take-home message? This is our Ka. or KB. So I do an ice table here, right? KB would be here. Do an ice table here, and then KW. I had to solve this simultaneous because the hydronium has to match here, and the hydroxide has to match with KW. And so all three have to be solved to a hydronium and hydroxide that satisfies all three equations at the same time, simultaneously satisfies all three equations. And so is this where I left off? So I set up 3 ice tables and then solved those 3 simultaneously. Yes? And so basically in number 1 and number 2, I have to solve those simultaneously. All 3. Ka, Kb, and Kw. But for this one, I don't. Why? The question is, do I need to solve it simultaneously? The answer is no. Why don't I have to solve this one simultaneously?
The pH equation that you gave us earlier?
No, that doesn't work here. The pH equations I gave you earlier, except the Henderson-Hasselbalch one.
Something over 2.
No, that one doesn't work. That one doesn't work here because that only works when you're dealing with an amphoteric. The base and the acid are the exact same species. Then you get that simplified equation. It's not the common ion effect. That's not the reason. It is common ion, but the reason is these are conjugates. And since they're conjugates, they're related. Whereas ammonia and acetic acid or ammonium and acetate, are those conjugates? No, those aren't conjugates. Those are unrelated, right? Dihydrogen phosphate and dihydrogen phosphate, they're related. They're the exact same thing. And so in this case, they're related because they're conjugates of each other, which means that I can solve either of these. And so Ka or Kb, but not both. In 1 and 2, I have to solve both, Ka and Kb. But in 3, I don't. Just one or the other. Why? It's redundant, yeah. It's redundant because if you look at the Ka and the Kb, they're the same equilibrium. Do you see that? And so it's redundant. It's described the same equilibrium. So one or the other is okay. Whereas in weak acid, weak base solutions, number 1s and 2s, the Ka and the Kb are not redundant. They describe different equilibria. And therefore, those have to be solved. Did we solve the ice table for Ka? Yeah? And we got a pH? Yeah, if we solve the ice table for Ka and we get a pH, then we could repeat it doing Kb, we get the exact same pH. No different. And so we solve it And so if we did that, I'm not gonna do it again here, but what we'll do is we'll just do a generic one. We call HA our generic acid, and conjugate base, which would be A minus. We can come up with a table. And so Ka or Kb is okay, but we're going to choose Ka. This is more convenient because it gives us hydronium rather than hydroxide. In other words, pH rather than POH. And so what we're going to have here is HA plus H2O liquid. It's going to give us H3O plus A minus. For this to be a mixture, we have to have significant initial concentration of HA and a significant initial concentration of A minus. And we're going to assume nothing's happened. We just have a mixture of weak acid and weak base present initially. And so one way we could do this is we can just take some acetic acid and mix in some sodium acetate, or any weak acid on that chart. And so the change here is going to be minus X molar, plus X molar, plus X molar. And so at equilibrium, we're going to get HA initial minus X. I'll just call it X. I'll just drop the units. And then over here, this is going to be A minus initial plus X. Maybe X smaller. Ka is going to equal the hydronium ion concentration at equilibrium times the A minus concentration at equilibrium divided by the HA concentration at equilibrium. Okay, the hydronium ion concentration at equilibrium is just X. The A minus concentration at equilibrium is A minus initial plus X. And then the HA concentration at equilibrium is just the HA concentration initial minus X. Then we just go ahead and use the simplifying assumption. If we use the simplifying assumption, then A minus initial plus X is just equal to A minus initial. So this is going to be X times A minus initial. And HA initial minus X is just going to be HA initial. Then we're going to take the negative log of both sides. In other words, we're going to do the power function. And so we get the negative log of Ka is equal to the negative log of X A minus initial over the HA. So this is going to equal negative log of X plus the negative log of A minus over the HA. Both of these are initial. And so the negative log of Ka is called the pKa. The negative log of X would be the px function, but we know what X is. X would be the hydronium ion concentration at equilibrium. And if we assume that we aren't going to get much, we assume Kw is a negligible contributor. Another thing we're going to assume. Assume Kw is negligible contributor. If Kw is a negligible contributor, then all the hydronium present in solution is going to come from this step. You know, we could ignore any additional hydronium that comes from Kw. then this is the negative log of the hydronium ion concentration at equilibrium. Plus the negative log of the A minus over the HA. All right, what is the negative log of the hydronium ion concentration at equilibrium? The pH. Okay, and then this is going to be minus the log of this A minus initial HA initial. And therefore we get this equation. The pH is equal to the pKa plus the log of the A minus initial over the HA initial. In other words, A minus is the base component, HA is the acid. So this is going to be the pKa plus the log of the base to acid ratio. The base and acid, these have to be conjugates of one another. In other words, they have to be conjugate pair. This is the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation just says that the pH is equal to the pKa plus the log of the base, the initial concentration of the base over the initial concentration of the acid. Therefore, since this is initial concentrations, we don't have to do the ice table. Here. Ice table is not needed, we just plug in the initial. So we don't have to figure out what the change is. And why does that work? It works because of the common ion effect. If you look at it, we expect the change to be small, as we've seen. Therefore, we don't lose much one way or the other. Or gain much, you know. We can do the same thing with Kb. For Kb, but it's redundant, right? You could do the same thing for Kb. It's redundant because rather than pH, we're going to get the POH. And POH is going to equal to pKb plus the log of the acid initial over the base. Initial. And so we do one or the other. That's it. So whenever we have a buffer that has an acid and a base that are conjugates, then we call that a Henderson-Hasselbalch buffer. And so let's take a look at Henderson-Hasselbalch buffers. So for the concept, one of the concepts for a Henderson-Hasselbalch buffer is the optimum pH, which we talked about here. So looking over here, we see if we have a 1-to-1 ratio of acid to base, then we're going to get these pHs here in that mixture. It's very easy to determine the pH of a 1-to-1 mixture. Over here, these are amines. Amines are bases, organic bases, and they show us the pKb. So we could use this this equation too, for the POH. These would be the POHs here. But what I do instead is I probably do this. If I have ammonia, the conjugate acid is ammonium. And the conjugate acid, well, it's going to give me a pKa of 14 minus this. And so 14 minus 4.74 is 9.26. And so the pKa of ammonium is 9.26. And therefore, a one-to-one mixture of ammonium to ammonia will have a pH of 9.26. pH of 9.26 means the base is dominant. And so ammonia is the classic organic base here with nitrogen. I say we're inorganic. These are organic here. And so we look, a typical hydrocarbons are electron rich. And so something like C2H5 is electron rich. We call it electron pushing group. So this is going to push electron density out onto the nitrogen, making it more basic. And so if we have these ethyl, like one ethyl group here, makes it more basic. Two ethyl groups makes it even more basic here. So pKb goes down, that means the Kb goes up. If we put a OH group on the amine or the ammonia, well, OH is an electron withdrawing group that sucks electron density out. And so that makes it less basic. And so the pKb goes up, which means the Kb goes down. Here, you can see it here. So we'll look more at this in terms of structure, but you can see patterns already emerging based on structure, looking at a table like this. All right, so what we want to do is look at this. For example, if I wanted a buffer of pH 7, I don't see that here. And so what I have to do is, if I want to be a pH of 7.00 for a buffer, I got to look for some acid that has a pKa of 7.00. Do you see it? No, so sometimes what we have to do is we have to adjust the pH. How can we adjust the pH? We can adjust the pH by altering the ratio. If we have a 1-to-1 ratio, we'll get this. But if we add more acid, the pH goes down. If we add more base, the pH goes up. And so there's a little bit of adjustability in this. And so how much adjustability? And so the pH of a buffer is adjustable. And so let's take a look at the range terms of how much we can adjust it. Let's say if we adjust the pH 1 unit higher or 1 unit lower than the pKa. Then we look at the base to acid ratio. The base to acid ratio is if we go +1, then the log of something has to give us 1, and the base to acid ratio has got to be 10 to 1, because the log of 10 will give us +1. And so we get 10 parts of base to 1 part of acid. Versus if we go -1, then it's 1 to 10. We have 10 parts more acid. And so if we had 10 parts more acid, we can drop the pH by 1 unit. And so, for example, here, if I have a 10 to 1 ratio of acid to base, the pH would be the pKa -1. 9. Let's go with a pH equal to the pKa of ±2. If I want a +2, then that means the base to acid has to be 100 to 1. Or if I go -2, it's got to be 1 to 100. Oh, so that's easy. Right? And so let's say I want to drop the pH by 2 units. So let's say I have 10, but I want 8. If I want 8, then what I can do is I can make the base 1 and the acid 100. And so that's easy. I just make the phenol 100 molar and the phenoxide, sodium phenoxide, 1 molar. Does that work? Have you ever seen a 100 molar solution? No. Why? You can't make it. It's way too concentrated, right? What is the molarity of pure water? Molarity of pure water is 55.5 molar. Well, I don't want 55.5 molar. I want 100 molar water. Can you make it? Impossible, right? It's not possible. You can't cram 100 moles of water into a liter. Because pure water is only 55.5 molar. And so we have a problem. So rather than making it 1 to 100, I go, okay, I'll make the acid 1 molar, and that means the base is 1/100th molar. Oh, that's easy to make. But there's a problem here because the base is starting to get too dilute. And so we limit it to this range. Because if we go outside that range, you know, if we do, let's say, +3, -3, we're looking at 1,000 to 1. And you certainly aren't going to make a 1,000 molar solution. It's not going to happen. And so if we make this one 1 molar, then this is going to be 1/1000th of a molar, which is nothing. 1/1000th of a molar. And so limit it to this range because the solution becomes too heavily biased. One-sided. You know, it's either dominantly acid or dominantly base and very little of the other component. And a buffer should have significant quantities of both components present. And so we try to limit it to a range of + and -1. And so if I try to make a pH 8 buffer using phenol and phenoxide, it's not going to work. You know, it's going to have way too much acid and very little base. And so I have to look at something else. Well, I could use hypochlorous acid. If I use hypochlorous acid and sodium hypochlorite, then that's within the range. I could get a pH 7 buffer. Well, let's see what kind of choices we have for making a pH 7.00 buffer. And so I'm going to go into the appendix here and see. Appendix D. Do you see some acids with a, well, here they don't have the pKa's. If they don't have the pKa's, we just look at the power. So this would be around pK of 5, right? pK of 5. Oh, here's one. This has a pKa of 7.00. And so this would be perfect. The acid would be H2ASO4-, and the base would be the conjugate base of this, which is HASO4 2-. So if I have a 1-to-1 mixture of these, acid and base, then it's going to make a versatile buffer. You know, equal components of both acid and base with a pH of 7.00. So this turns out to be perfect. A 1-to-1 mixture of this will give us a pH of 7.00. But this isn't a good one. Why? Because what is this called? This is called dihydrogen arsenate. Dihydrogen arsenate is quite toxic. And so we probably wouldn't use this, arsenic being very toxic. So is there something else? Close or right on? Carbonic? Carbonic is very close. Carbonic is very close, but can you go buy a bottle of carbonic acid? You know, let's say I'm on a 6 molar bottle of carbonic acid. No, you aren't, because carbonic acid is unstable, decomposes in water and CO2. So you aren't going to be able to get a very high concentration. So carbonic is not going to be good. Oh, here's another one, this monohydrogen citrate. Monohydrogen citrate with citrate. But there's a problem with this buffer, and that is citric acid. It decomposes. Citric acid is pretty electron rich. It's easily oxidized. Decomposes. Hydrosulfuric acid is perfect. 1.0 times 10 minus 7, which is a pH of, or pKa of 7.00, which would give us a pH of 7.00 with a 1-to-1 mixture of H2S and HS minus. That would be perfect. Except for 3 things. One, the smell of H2S is awful. It smells like rotten eggs. And so H2S, the smell is very bad. Number 2, it's highly toxic. H2S is part per billion of H2S gas can kill you. Number 3 is H2S isn't very soluble in water. The solubility of H2S in water is only 0.1 molar, which means the maximum concentration we can get of H2S is 0.1. So that's not good. What we're looking for is something that's non-toxic, hopefully, or not too toxic, and preferably cheap. And so let's go down the list here. Maybe malonic, hydrogen malonite. That's a little too far. 10 to the minus 5. We need 10 to the minus 7 or closer. See anything close? This is pretty close, 6.3 times 10 to the minus 8, you know, because if this were 10 times 10 to the minus 8, 10 times 10 to the minus 8 is 1 times 10 to the minus 7, which is perfect. And so this is very close. This is dihydrogen phosphate. So if we take dihydrogen phosphate and monohydrogen phosphate, we could make a buffer from that. So let's try that. And phosphate's pretty common, right? And not too terribly toxic. So what we want to do right now is we want to try to make a 7.00 buffer. So we want a 7.00, pH 7.00 buffer. The acid we chose is dihydrogen, well I chose dihydrogen phosphate, because the pKa of that is going to be the negative log of 6.3 times 10 to the minus 8, which is 7.20. And just slightly high. It's just slightly high, so we just need to add a little bit more acid than base, and we should be okay. This is a Henderson-Hasselbalch buffer, and so the pH is going to equal the pKa plus the log. Okay, if this is the acid, then the base component has got to be HPO4 2 minus. And so it's going to be the base, HPO4 2 minus, over the acid is H2PO4 minus. This is going to be the pKa of the acid, H2PO4 minus. And so this is going to be The desired pH is 7.00, so we'll just plug in pH is 7.00. That's what we want. This is going to equal the pKa, which is 7.20, plus the log of the base to acid. And so the log of base to acid, I'll just call it B over A, save time, is equal to minus 7.20 from both sides, so minus 0.20. And therefore the base to acid ratio is going to equal 10 to the minus 0.20, which is equal to what? .63. Give me one more digit. 0.630. And so that means I need 0.63 parts of base to every 1.00 parts of acid. And so what I can do is I can make this 0.63 molar and 1 molar. And then I should have a pH 7 buffer. Or, can you invert this so that we get 1.00 over what? 0.58. Or if I invert that, if I make the base 1 molar, then the acid should be 1.58 molar. Or whatever ratio works, give us the same 0.63 to 1. Let's use this because it's easier, I think. And so if I make the base 1.00 molar, and so I need the base, which is HPO4 2 minus, to be 1.00 molar. And that means the acid, H2PO4 minus, will be 1.58 molar. Then this solution should have a pH of 7.00. All right, I'm going to take 100 mils of this. And then see how this buffer responds to added acids and added bases. And so here, I have this buffer. I can add strong acid, such as HCl. If I add HCl to this, then what happens is the base component, which is HPO4 2 minus, will neutralize that. And so the HCl will react with the HPO4 2 minus to form H2PO4 minus and chloride. And so as long as I make sure I have excess buffer, I can neutralize the acid. When I neutralize the acid, I don't make salt and water though, I just make a weaker acid. And so it's taking out the strong acid and replacing it with a weaker acid, H2PO4 minus. If I add strong base, this buffer will neutralize that too. So for example, if I add sodium hydroxide, then the acid component in the buffer, HP2PO4 minus, will neutralize that to form HPO4 2 minus and water. And so I take a strong base like this and I convert it into a weaker base because this is neutralization. It doesn't go to pH 7, but it just neutralizes it. And so let's do an example here. I'm going to add 1 drop of 6.00 molar HCl to this buffer. And so this would be the buffer here, and then I'll just add 1 drop of 6.00 molar HCl. When we took an unbuffered solution like water or sodium chloride or whatever, the pH changed dramatically. 4 pH units change, which would be 4 orders of magnitude difference in acidity. So chapter 17 problems, what we're going to do is we're going to do solution dilution. So what we'll figure out first is the final volume, which would be 100.05 milliliters. And then we have to figure out the new concentrations of everything before we do any reactions. So HCl is going to be a 0.05 to 100.05 dilution of 6.00 molar, which gives us, what was that, 1.5? 1.58 times 10 to the minus 3 molar? Was that it, or 1.2? I thought it was 1.20. Tweed, do you have that number? The HCl from before. 1.20, was that it? 1.20 times 10 to the minus 3 molar after the solution dilution for the HCl. It's the same dilution factor, so it's the same calculation. All right, then we figure out the new concentration of HPO4 2 minus. HPO4 2 minus is going to have a dilution factor of 100.0 over 100.05. That. This was 100.0. And the concentration of this is 1.00 molar, which is, this is barely diluted. It's a 100 to 100.05 dilution. Almost the same thing. And so what does it come out to here? To 0.99. Yeah, give me more 60.
95.
Okay, 9995?
Yeah.
Okay.
0.
0. That should be enough. Uh-huh.
Earlier that the one we gave, we used 0.02 over that, and this one you use 0.05. So if it was 0.05, you get 0.99.
Wow.
Yeah.
Then the earlier one, I made a mistake because it's not 0.02, it's 0.05. It should be 0.05. Can we correct that one? Then it would be 2.99 times 10 to the negative 3 molar. Which means the earlier one, if we correct it to 2.99 times 10 to the minus 3, the pH comes out to about 2.5. Is that correct? Yeah. So it's still about, 4 orders of magnitude change in acidity. Okay, then we go to H2PO4 minus, which is going to have a 100 to 100.05 dilution times 1.58 molar. This gives us what for the diluted concentration? $1.579. 1.579. Give me more digits. One more. 2. One more digit. 1. Thanks. 205. Just carrying out more places because of this. That's it. All right. So before we do anything, we call this step I. Step I is this solution dilution. We just figure out, this is the new total concentration, what are the concentrations of everything in it? Okay, once we do that, then we'll do step 1. In chapter 17, as in chapter 16, the step 1 is the same. Step 1, we take the strongest acid plus the strongest base present. And so we look for what's the strongest acid present in this mixture. It would be HCl. What's the strongest base present in the mixture? Yeah. Even though both of these are amphoteric, monohydrogen phosphate's amphoteric. You go either way, it could be an acid or base. Dihydrogen phosphate's amphoteric.